Hi, myself Kantraj, Assistant Professor of Physics, Government First Aid College, Malur. This is a class for BSc Physics, third semester, Bangalore University North. The title of this paper is Electricity and Magnetism. So for this session, we are going to discuss about a charging and discharging of a capacitor in a simple RC circuit excited with a DC source. And also we are going to discuss about a time constant of RC circuit. These are the learning objectives of the chapter. So the main outcomes of this chapter is students can understand the transient response of a CR circuit for charging and discharging of a capacitor, and also the transient behavior of electrical network for various circuits, and we can able to find out the time constant in CR circuit. So let me see about the concept of CR circuit. Before knowing the concept of growth in CR circuit, already we have seen the last session, it's LR circuit, that is inductance and resistance in series. So in both the cases, the growth and decay. So as the inductive circuit, which is a very important point, is the current, which I am going to say about a current. The current is maximum, or the expression what you got in the terms of your current I is equal to I naught 1 minus e to the power of minus L divided by R into T, where T is called as a time constant, and that T represents the tau, which is equal to L by R. So the tau, whenever the tau is nothing but L divided by R, it suppose T is equal to tau L by R, which shows that 63.2% of the maximum value can store in a inductor. Similarly, when you come to know about decay, so that is the initial value what is stored in the magnetic field energy current, maximum I naught, that can be discharged for L by R, that is T is equal to L by R, means that 0.36.368%, that is 36.8% of your initial value which is taken the fall. So this is the case which you have studied in your LR circuit. The similar way which I am going to explain about the CR circuit. So in the CR circuit, that is capacitance and resistance, which is takes place both the characteristics. One is called growth of charge in circuit, CR circuit, or simply we can say that a charging of a capacitor in CR circuit. Similar the way we can explain the decay of charge in CR circuit, or we can say that discharging of a capacitor in CR circuit. So as we look on the components like it is a resistor or capacitor or inductor, so the passive components in that capacitor is also one of the type of passive component which used for charging, as well as we can use for discharging of the capacitor whenever you want. So when you see about the circuit, a circuit consists of an uncharged capacitor and the resistance R, if it is connected with a series of a battery of EMF E volts with negligible internal resistance with a plug key. So once the key is said to be closed, that is key is closed, the capacitor is charging up and the charging current flows in the circuit. Once the key is said to be X and Y mode, or the press to the XY mode, the current is charging up and the charging current flows in the circuit. The charging current is maximum at the instant. The charging current in the capacitor is maximum at the instant of switching and decreases gradually as the voltage across the capacitor increases. The current will be decreases as the voltage gradually increases. When the capacitor is charged to the applied voltage E, the charging current becomes zero. So this property which is show about the case, it's called as charging condition or a growth of the charge in the CR circuit. So when you look about this the diagram, you want to calculate the time constant of the circuit. So we are going to calculate the time constant, means we have procedure for that. So let whatever the charge will be having in the capacitor, let Q will be represent the capacitor charge. Let Q be the charge on the capacitor. Then what is the potential difference across it means we know that basic equation Q is equal to or V is equal to Q divided by C. So the voltage drop across the capacitor, we can write that Vc is equal to Q, the total amount of charge divided by capacitance. So let I be the current, in the same instant of time. Then the potential drop across the resistor, which I can say that it is I into R, the potential drop across the resistor. According to the KVL, Vc plus Vr is equal to E, that is voltage drop across the capacitance plus voltage drop across the resistance is equal to the total EMF of the circuit, because it is a closed circuit. If you close circuit, if you apply the KVL, Kirchhoff's voltage law, the total EMF in the circuit is equal to sum of the potential drop across each elements. So when you are substituting the value of what is Vc is equal to Q divided by C, and what is the voltage drop across the resistance? I into R, which is equal to E. And relating the expression, that is when you see about your what you called as I is equal to dq divided by dt. So I into that is R into I means dq by dt, E minus of Q divided by C, we can rewrite the expression. R dq by dt is equal to EC minus of Q divided by C is an expression. So once if we have the terms of dq and dt, so there will be equating the equation in the form like what is dq by EC minus of Q and is equal to dt divided by CR. So now we get the equation, the terms of charges and with respect to the time. Now we are going to integrating the equation on both sides with certain limits. So log of integration of dq divided by EC by minus Q, which represents as log of, this is the integration of EC divided by minus of Q, dq divided by EC minus Q is equal to log of EC minus of Q. And 1 by CR you take outside, integration of dt is nothing but t. So taking this equation, log of EC minus of Q, because minus is there, so I can represent minus of Q EC minus Q is equal to T divided by CR plus of K. Why I am getting the minus sign means when you substituting the value of when you taking the value of EC minus of Q, it is in the minus term. So log of, that is minus of log EC minus Q will get. So I can write this equation minus log EC minus Q is equal to T divided by CR plus of K, where K is called as integration constant. So substituting the boundary conditions, when K is integration constant, whose value can be determined for the initial conditions. What is the initial conditions? We can state when capacitor, whenever the time is equal to 0, the charge in the capacitor will become 0. Is it right? So when t is equal to 0, q is equal to 0. Then the equation, if we substitute these values in the equation 1, we'll get k is equal to minus log into EC. So once if we get the integration constant, substitute the integration value constant in the above equation, then minus log EC minus Q is equal to T divided by CR minus of log EC, or log of EC minus Q minus of log of EC is equal to T divided by CR. This is nothing but log of A minus B, that is log M by N form. So if I am substituting here, log of M is EC minus Q divided by N is EC, which is equal to minus T divided by CR. So now 1 minus Q divided by EC, taking the log to that side, so it will become exponential. So 1 minus Q divided by EC is equal to e raised to the power of minus T divided by CR, or Q by EC, substituting, I mean taking the 1 to that side, or minus e to the power of minus T divided by CR this side. So that is Q divided by EC is equal to 1 minus of e to the power of minus T divided by CR will get. So when if you take the value of maximum amount of charge has been stored in the capacitor, so the potential across the given capacitor, whatever we are going to take E into C, that is nothing but it is the amount maximum charge in the capacitor for a given time. So it's a Q naught is equal to EC. Substituting the value of Q naught is equal to EC, Q is equal to Q naught 1 minus e to the power of minus T divided by CR is an expression for your capacitance, the charge on the capacitance or the charging condition of a capacitance. So final steady maximum, that is EC is equal to Q naught, means it is represents that the final steady maximum charge on the capacitor. So this equation, it is representing the charging at any time during the charging. Q is equal to Q naught E1 minus e to the power of minus T divided by CR. So when you see about this expression, it also shows that the charging exponentially increases. If T is equal to CR, then Q is equal to Q naught 1 minus 1 divided by E. So which is equal to 0.632 Q naught. Substituting the value of E, so 0.632 into Q naught, where CR is called as time constant. Now then when you look about your LR circuit, L by R is called as time constant. Now we are going to take that C into R is called as time constant of the circuit. It is defined as the time required for the capacitor to charge to a 63% of its maximum value. That means once the capacitor is set to be switch on, so it will take some time to charge the value of 63.2%. So that time, it is nothing but a time constant. It is the product of C into R. It's called as time constant. Its value is denoted by lambda, or thus lambda is equal to CR. When T is equal to 5 lambda, then Q is equal to 99.99% of maximum value which are stored in the capacitor. So that is 0.995 Q naught. Hence, we can assume that the capacitor is said to be fully charged. Similarly, when you want to know about your current wise, I am talking this up to this, it's charge. The current is given, usually we know the definition of current, I is equal to dq divided by dt. So what is Q? Q is substituting the value Q naught 1 minus e raised to the power of t divided by CR. So if we differentiate this equation, we'll get that I is equal to Q naught by CR e raised to the power of minus t divided by CR. So Q naught divided by CR, I can take it as some value of I naught. When t is equal to 0, then I is equal to Q naught C by CR. The current decreases exponentially the growth of charge and the decreases of current as shown in the figure. So once the charge is said to be exponentially increases, so at the same time what I said in the beginning, as the capacitor is said to be the fully charged, means the current will become zero, almost zero, or initially it starts increasing, so that shows about the current goes on decreasing with respect to the time. So looking these two diagrams, we can explain that. So what happens the charge when initially, and what happens the current if it is a maximum value of current, if increasing the time, the current will be decreases, and the amount of charges which is going to charge on the capacitor, it is a maximum value. So this way I can explain that the two important graphs which shows about your time constant, that we can represent that I is equal to I naught e raised to the power of minus t divided by CR is an expression for current in the case of growth. Similarly, when you take about the decay, so usually whenever the capacitance is going to charge, so when you see about any electronic system, if the capacitor is going to charge, so at a certain time it should be discharged. So for that, let us see that initially when the capacitor is fully charged, now the switch is set to be XY, that is X and Z. I am going to contact with X and Z. So in this loop, in this network or a closed loop, we don't have any EMF in the circuit. the capacitor is charged through the maximum value, it is Q naught, and now it's began to discharge through the resistance. So the switch is thrown to the position 2, the capacitor was charged to Q naught, is now began to discharge through the resistance. Since there is no EMF in the circuit, we just write that is applying the KVL for this loop, Q by C plus I into R is equal to 0. That means what is the value of capacitance, voltage drop across the capacitance or voltage drop across the resistance. So we can write that Q by C plus of I into R is equal to 0, where Q is a charge at any time. So that is Q by C plus R into dQ divided by dt. So which implies that dQ by dt, that is dQ by dt is equal to minus Q divided by CR. Or simplifying this equation, taking the terms of dQ at one side and 1 by CR into dt to another side. So if we have the expression for dQ by Q and minus 1 divided by CR into dt, now you can integrate the given equation with both the sides. Integration of dQ divided by Q is equal to log of base C, that is Q, is equal to minus dt, means t times CR plus of integration constant. When you look at the boundary conditions, initially when you have a capacitance has been charged, t is equal to 0, at time t is equal to 0, what is the value of capacitance charge? Q is equal to Q naught. Hence, if we substitute Q is equal to Q naught and t is equal to 0 in this equation, then we can get that K is equal to log of Q naught. When t is equal to 0 and Q is equal to Q naught, hence K is equal to, that is log of Q naught, you will get the value of your expression. Substituting the value of K in the equation 1, then log of Q is equal to minus T divided by CR plus log of Q naught. So this I can write that sending towards this side, log of Q minus of log Q naught is equal to minus T divided by CR, or else log of Q divided by Q naught, which is equal to minus T divided by CR. So taking the log to that side, Q is equal to Q naught e raised to the power of minus T divided by CR is an expression for a decay of current. Where R is the time constant of circuit, then T is equal to C into R. Then we can write that is Q is equal to Q naught divided by E, and the current I is equal to dQ divided by dt. Substituting the value of Q value in this expression, we get that is I is equal to minus Q naught divided by CR e raised to the power of minus T divided by CR. So what I said, that I naught in the terms of previous case, the same way I is equal to minus I naught e raised to the power of minus T divided by CR, which is shows that Q naught by CR can be taken as I naught. So I substituting the value of here, so I is equal to minus I naught e raised to the power of minus T divided by CR is the expression for current. And for the charge, you can take that Q is equal to Q naught e to the power of minus T divided by CR. So when you see the discharge of a capacitor, as we look on the time constant to define, the time constant of CR circuit through the decay is that during the time which the charge of capacitor decays to 37% of its initial value. So looking at the graph here, once the capacitor is fully charged, for example T, which is equal to lambda is equal to CR. So if the CR value, it supposed to be taken as 1 C into R, some value, so that will decreases the value of 0.37 times the Q naught value as initial value. If we go on increasing the value of capacitance under a resistance or time taken for 1 times lambda, 2 times lambda, 3 times lambda, 4 times lambda, and finally if we come to the 5 t or 5 times t, the charge decreases almost 0. So this shows a curve which explains about a decay of current, decay of your capacitance charge on your capacitance. Thus the current decreases exponentially, but in the opposite direction, which are shown in the figure. When you take about your I is equal to minus I naught e to the power of minus t divided by CR explains that is current decreases exponentially but in opposite direction, which are shown in this figure. That is, when you take about your charge, if it is a maximum and with the value of your I naught, it's going to decreasing, shows that the curve represents the as minus represents the exponentially, it's go on decreasing. That shows that the given a diagram. So this way we are going to discuss, we have discussed charging and discharging. That can be said that it is called as decay and growth and decay of your capacitance. So these are the multiple choice questions. Let me discuss. In any RC circuit, when the switch is closed, the circuit is complete. What is the response? So seeing the response of that, we can explain that the explanation in any RC circuit, the response decays with the time because according to the equation, there is exponentially decreasing the response. So in any RC circuit, when switch is said to be closed, the circuit is complete. What is the response means? It always decays with the time. This is an answer for answer is B. The expression of current in RC circuit is, so when you take about your in the terms of current, I is equal to I naught e to the power of minus t divided by CR, where I naught is can be represented V divided by R. So in simplicity, V divided by R is equal to I naught. That you can show in the expression. The answer is B. The capacitance C is charged through a resistor. The time constant of charging circuit is given by either C by R, 1 by RC, or RC, or R by C. So looking back to the time constant in your charging and discharging of capacitance, we can write that C is your answer, that is RC. The charging time constant of consisting capacitor is time taken for charge capacitor to become dash percentage of initial value. When you take about your charging consisting of a time taken for the capacitance, so what is the value of charge? Initially it has been charged. So I told that when T is equal to, that is lambda R into C, the value of the capacitance going to charge 63%, decreases 37% of your initial value. It's going to time to decrease the value, so that is 37%. So these are the references we have took on the for this class. So I Omkar Publications with Basavaraj and Sadashiv, and Sunstar Publications, Dr. Jaishila and Vazia Sultana, and H.C. Manjunath and Dr. Vidya. So and also some few of the internet resources. So this is the class. Thank you one and all.